Okay, right. Okay. Now, if I just summarize, last class I think we have discussed about the different types of sensors. So 4 different classification of sensors we have discussed, if I am correct. So null type sensors, deflection type sensors, and then displacement, position, and proximity sensors, then contact and non-contact sensors, and then the thermal, electromagnetic, mechanical, chemical, and optical sensors. Okay, right. Now everything is visible clearly.
Yes, sir.
Okay, right. Now in this case, right. Now we'll proceed with what is called as the all effect sensors. Okay. So now, before we go with all effect sensor, first you note down that all effect sensor is a type of a magnetic sensor. Okay, is a type of magnetic sensor which is mainly used to determine the magnetic flux density. Okay, so all effect sensor is mainly used to determine the magnetic flux density. Now, what exactly is the statement of all effect sensor is what is important. Okay, class. Okay, so the all effect statements, all effect states that class class class. Okay, all effect states. Okay, now a voltage is generated perpendicular to current flow in a magnetic field. Okay, now what does it mean? Please understand carefully. The all effect states that a voltage is generated perpendicular to the current flow in a magnetic field. That means in case of the all effect, the basic concept of all effect is nothing but if you consider any conducting material. Can you able to hear me clearly? Yes?
Yes, sir.
Yeah, good. Okay, in a conducting material, just assume we have a conducting material. Now to that conducting material, what I am going to do is I am going to pass the current. Okay, just remember we have a conducting material. I will pass the current to it. Now to this conducting material wherein the current has been passing, I am going to apply the magnetic effect. Okay, I am going to place a magnet, a permanent magnet near this conducting material. When I am going to place a permanent magnet near a current carrying conducting material, there exists what is called as a voltage. A voltage is going to be generated. How the voltage is going to be generated? The voltage will generate perpendicular to the current flow. The voltage will generate perpendicular to the current flow in a magnetic field. And this effect was identified by a person by name E.R. Hall, and hence this effect is called as the Hall effect. Okay. Now, what is this? Much more understanding of this is very important. Now, if you observe carefully, now what is the basic principle of Hall effect? It says all effect sensor work on the principle that when a beam of charged particles passes through a magnetic field, okay, a force acts on the particle and the current beam is deflected from its straight line path. Okay. Now, before that, you just observe. Now we have what is called as, right. Now just observe here. Okay. Right. Now we have what is called as observe carefully. A current carrying conductor is going to be there. Right. Now for this current carrying conductor, I am passing the current. Okay. So the conducting material is going to be there. To this conducting material, I have passed the current. When I pass the current, what is going to happen is the electrons are going to move. Okay. The electrons are going to move. Let's say if I have passed the current from here, the electrons are going to move in the electrons are going to move generally. Okay. You know that the movement of the electron is nothing but the movement of the charges. Is it not? So when the electrons are going to move, it means that we will say generally that the current is transferring or the current is moving. Okay. Now this is what is the regular path. Now what is the path of the charged particle? Is it a deflected path or is it a straight line path? Hello.
Straight line path.
Okay. In the initial case. Okay. In the initial case, the charges are going to follow a straight line path. Now, what is the condition at this point now? I have a conducting material. To this conducting material, I have passed the current. When I have passed the current, the charges are going to move in a clear straight line arrangement. Okay, so this is the first case number 1. Case number 2 is what? To this, I am going to apply a magnetic field. Means what do you mean by applying the magnetic field? It's simple, that I am going to bring a magnetic material near this conducting material. Okay, when I am going to bring a magnetic field, some effect is going to occur. Okay, what is that effect? That effect is it deviates, okay, it deflects the charged particles, okay, towards one particular area. That means those who are moving in a straight line manner, the effect of this magnetic field is to see that the particles are going to be deflected. The particles are going to be deflected towards one particular end. Okay, therefore, what is going to happen now? These charges will flow like this. Okay, when the charges are going to flow, what is going to happen? The charge separation is going to occur. Now here what has happened? There will be collection of what? Collection of negatively charged particles is going to occur at this point in time, or at this area. More amount of negatively charged particles are going to occur, and the opposite one we call it as the positively charged. Now what I will do is I will place the meter. Okay, when I place the meter in between, okay, that is our the multimeter in between this point, okay, and this point and this point. Okay, now there exists what is called as a reading. Okay, that reading we are going to get what is called as a voltage. Okay, that is what is called as the development of the Hall effect. Okay, now that is what is that I have shown here. Okay, just observe. Okay, the Hall effect states a voltage is generated perpendicular to the current flow in a magnetic field. Now, the deflection of path of charged particles, observe carefully, the deflection of path of charged particle from its regular path due to the influence of the magnetic field is called as Hall effect. Okay, now what we have now is we have what is called as a regular path. Okay, now this is what first one was the regular path, other is what is called as the deflection of the path. Now regular path is going to be there when there is no magnetic effect. The deflection of the path is going to occur whenever the magnetic field is going to be present. This effect is called as the Hall effect. Okay, right. Now you can observe clearly now here why this effect is going to be. Now when you bring this is very important, when you bring the magnetic field, there is some force which is going to act. Okay, forces are act on the particles. Okay, what type of force is this called as? This force is called as the Lorentz force. Please note down. Okay, the force which is going to act on the particles with the influence of the magnetic field is called as the Lorentz force. What this Lorentz force does is, this Lorentz force will attract the charged particle which are moving in a straight line path, okay, towards one particular direction, and that direction we call that as the negatively charged particles. Okay, right, that is what is going to happen. That one side of the disk, now you can understand here, one side of the disk will become negatively charged and the other side will be a positively charged. Okay, so this charge separation generates a potential difference. This is very important. This charge separation generates a potential difference. This is nothing but, okay, the amount of voltage generated is a measure of the distance of the magnetic field from the disk carrying current. Okay, that means now if you are going to bring the magnet very near to the conducting material, what is the potential difference? Will it be more or will it be less? Okay, it is going to be more because you are bringing the magnetism or the magnetic effect nearer to the conducting material. Hence, there will be more potential difference. That means what? If you take the magnet away from the conducting material, the voltage generated is going to become lesser and lesser. If you bring the magnet nearer to the conducting material, the voltage generated is going to be more and more. So this is the basic understanding. Okay, now you can observe this diagram, or else just observe this video. Okay, just observe carefully this video, then you can able to understand. Okay, so what exactly is the concept of the Hall effect. Okay, can you able to see the video? Yes or no? The video?
Yes, sir.
Yeah,
Yes, sir.
please watch the video.
Hello, Daniel Luxky here from howtomechatronics.com. In this video, we will learn what is Hall effect and how Hall effect sensors work. The Hall effect is the most common method of measuring magnetic field, and Hall effect sensors are very popular and have many contemporary applications. For example, they can be found in vehicles as wheel speed sensors, as well as crankshaft or camshaft position sensors. Also, they are often used as switches, MEMS compasses, proximity sensors, and so on. Now we will go through some of these sensors and see how they work, but first let's explain what is the Hall effect. Here's the experiment that explains the Hall effect. If we have a thin conductive plate as illustrated and we set current to flow through it, the charge carriers would flow in a straight line from one to the other side of the plate. Now, if we bring some magnetic field near the plate, we would disturb the straight flow of the charge carriers due to a force called Lorentz force. In such a case, the electrons would deflect to one side of the plate and the positive poles to the other side of the plate. This means if we put a meter now between these two sides, we will get some voltage which can be measured. So the effect of getting a measurable voltage, as we explained above, is called the Hall effect, after Edwin Hall, who discovered it in 1879. The basic Hall element of the Hall effect magnetic sensors mostly provides very small voltage of 1.
Okay, right. Is it understandable? Clear?
Yes, sir.
No. Okay, right. Now that is what is that. Now if the diagram still I can able to make you to understand. Now in this case, what has happened? Okay, right. Now if you observe this diagram clearly, now we have what is called as a picture which indicates. Okay. Now forget about this magnet now. Okay, just forget about this magnet. So without the presence of this magnet, what is going to happen is these charges are going to move in a straight line manner. With the presence of magnetic field, there will be the movement is going to occur, which develops what is called as the Hall voltage. Okay, now this is the basic principle of the Hall effect sensor. Okay, right. Now we'll try to understand what is the magnitude of the EMF which is going to be developed. Okay, now we have just told that there exists what is called as a voltage. Okay, voltage is going to be generated. Okay, voltage is going to be generated. Okay, perpendicular to the current flow. Now we'll try to understand what is the voltage which is going to be generated and on what parameters it is going to be present. Now you can observe clearly the amount is going to be, okay, the amount magnitude of the EMF produced, okay, depends upon, okay, number one, current, okay, that is current passing through the conducting material. Next one is the amount of magnetic flux density. Next one was thickness of the plate, and then the property of the conducting material called as the Hall effect coefficient. Okay, now if you go with the equation, okay, now V is proportional to, okay, so once again, okay, okay, right. Now just observe here, yeah, okay. Now, okay, V is the potential difference is given by what? The potential difference voltage is given by VH is proportional to BI by T. Okay, now this is the equation. So what is VH now? Okay, VH is nothing but your Hall voltage. Now, if I remove the proportionality constant, the proportionality constant is going to be what? Is going to be KH, which is the Hall voltage, and same BI by T. Now, VH we know it is Hall voltage, KH is the Hall effect coefficient, B is the magnetic flux density, I is the current through the plate, and T is the thickness of the plate. Now, what you need to understand here is, okay, a few things, please listen carefully. Now, for a particular conducting material, okay, if you assume this is going to be a conducting material, okay, now the thickness of the conducting material is going to be constant. Okay, the thickness is, this is called as a thickness. The thickness is going to be constant. Okay, right. Now, as the material is going to be same, okay, obviously the Hall effect coefficient of that material is also going to be a constant. Okay. Now, which are the variable parameters here? Which are the variable parameters? In this equation, which are the variable parameters?
Current in the plate. Sir.
Current in the plate and also
Thickness.
huh?
Thickness, sir.
Thickness I have made it constant. Thickness is constant.
Flux density, magnetic flux.
Magnetic flux density. Okay, now if you just observe carefully, these two are the one which are varying factors. Okay, so these two are the one which are varying factors. Okay, now what I will do is the current passing through the plate, I will make it as constant. Okay, now I will keep the value of I is equal to constant. Okay, some 3 amperes or 4 amperes is the current what is that I am passing on. Okay, now the amount of voltage generated now, okay, the amount of voltage generated VH will now directly proportional to what? Will now directly proportional to what is called as the magnetic flux density. Now understand this equation carefully. VH proportional to BI by T. Now taking the proportionality constant, I will keep it as VH is equal to KH BI by T. For a conducting material, the value of KH is constant. For a conducting material, the value of KH is constant. So this will be eliminated. And thickness of the plate is also constant. That also I am going to take it off. And I will make sure that the current passing through the plate is going to be same. The current passing through the plate is going to be same. Hence, the value of VH is directly proportional to what is called as the magnetic flux density. Therefore, the change in the value, okay, change in the value of VH, okay, the change in the value of VH, okay, is directly proportional to what is called as the magnetic flux density. Now here, one thing that you need to understand, very, very important. Okay. Now I am telling, okay, all the time that I am going to use the conducting material. Okay, which are the conducting material that you can use? Example. Which
Copper, sir.
huh?
Copper.
Okay, right, copper, fine. Okay. When I say conducting material, okay, please understand, when I say conducting material, any material which conduct electricity can be used. Okay, which it is very clear. Any doubt here?
No, sir.
No. Okay. Now the next question is very, very important. Next question is, can I use any conducting material is the question. Okay. Now please understand the amount of voltage generated. Okay. The amount of voltage generated is very, 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 very smaller. Okay. Is very, very smaller if I am going to use metallic materials. Please understand. Okay. The amount of voltage, because the charge carrier is not going to be that much higher, by which the value of VH is going to be larger. Okay, the voltage generated is going to be very, very smaller if I am going to use a metallic conducting material. Okay, metals as the conducting material. Therefore, what is the other option for me is I am going to use what are called as, very important, semiconducting material. Okay, I am going to use what are called as the semiconducting material or semiconductors. What is the advantage of using semiconductors is important. Okay, the advantage of using semiconductor is that by using semiconductor, there is a possibility of what is called as doping. Okay, that means transferring the electrons into the material. Okay, this process is called as the doping. Okay, now if you remember the basic concept of your basic electronics, okay, the concept of basic electronics, so this is what is called, okay, called as the doping. Doping is nothing but what? Doping is the incorporation of the charged particle from outside. Okay, from the outside you can able to from the outside you can able to incorporate, or you can able to dope, okay, the external material. What is the advantage of this? If I am going to do the doping operation, what is the advantage?
Get more voltage.
Okay, now I am going to get more voltage. Why I am going to get more voltage? Simple. Okay, because the voltage depends upon what? The voltage depends upon the charge carriers called as the electrons. Are you understanding? How many electrons are going to be there? Okay. So if there are less electrons are going to be present, what is going to happen? The amount of voltage generated is going to be lesser. Now further what I am making is I am externally, from the external source, I am inserting more amount of electrons, more amount of charges into the material. When there is more amount of charges doped into the material, the charges which are going to be separated will have a more amount of energy. When they have more amount of energy, the value of VH is going to be more compared to the conducting material, which are called as metals. Okay, are you understanding now? So metals are not generally used as the conducting material. Rather, the semiconducting materials are going to be used. Okay. When I am going to use semiconducting material, the advantage is that enough amount of a good amount of the electrons can be doped into the material, by which the value of VH can be increased. Okay, now this is what is the basic concept of the Hall voltage. Okay, then let me just go with some of the applications of the Hall effect sensors. Okay, right. Now the applications of Hall effect sensors are, now it can be mainly used to detect the rotation speed. Okay, as you observed, now in all our the bikes and the car, you can able to have this sensor to be placed near the tire, so that we can able to determine the speed of the vehicle. Okay, and used for the movement detection movement, and one exam, and also used as a position and motion sensors. Okay, right. So one example I'll just try to quote here, okay, which is the fluid level indicator, or I can also call it as the fuel level indicator. Okay, now what is this example? Okay, please understand this example carefully. Right, now in this the fluid level indicator, what is that I am having is, I am having this one. This is called as a sensor. Okay, so this is called as a sensor. To this sensor, I have given the supply, the input supply I have given. Okay, and here I am going to measure the output, and one will taken to the ground. Okay, now I am having what is called as a float, because this member is called as what is called as a float. Okay, the float is going to move within this, right? Now at the top of the float, I have placed a magnet. Please understand. At the top of the float, I have placed a magnet. Okay. Now assume I am checking the level of fuel in the fuel tank. Okay. Now I am having a bike. Now in that bike, I just want to know what is the consumption of the petrol. Okay. Now this is a sensor. That is what is that I have attached there. Okay. Now, what is the effect of this magnet? Why this magnet is present here? To give what?
Deflection.
No. The presence of the magnet will gives you what?
Flux density.
Flux density. Okay, the presence of the magnet, that is, I will place some the permanent magnet. Some permanent magnet I am going to place. So due to the presence of the magnet, okay, I am going to get the magnetic flux density. Okay, supply is nothing but your current. I have given the current to it. Okay, now just observe the output I am measuring. What is the output that I am going to measure? What is the value of the output that I am measuring here? What is the value of the output? Voltage I am going to measure. Is it clear? Right. Now, I have started to use my bike. Okay. Right. What is going to happen with the amount of time? Okay. When I am on bike, when I am on my bike, what is going to happen to this float? Will it be in the same position?
No.
What will happen to the float? Float will?
Right.
Huh? The float will descend. Yes or no? Understanding?
Yes, sir.
The float will descend. Means the float will come down. Yes or no?
Yes, sir.
Right. When the float comes down, what is going to happen to the magnet? Magnet has been attached to what? Magnet has been attached to the float. Okay. Right. Along with the float, the magnet will also comes down. Okay. When the magnet comes down, what is going to happen to the value of voltage?
Decrease.
Huh?
Comes down.
Increases, sir.
The value of voltage is going to comes down. Okay. Now, the amount of reduction in the value of voltage depends upon what?
Flux density.
Depends upon the flux density. Okay. Depends upon how close this magnet is towards the sensor. Okay. Assume that it's a full tank. Okay. Under the full tank condition, the magnet is going to be, is it very close to the sensor or is it away from the sensor?
Close to.
When the tank is full, okay, correct? When the fuel is full in the tank, the float is going to be on the top, correct? When the float is on the top, the magnet which is attached to the float will be very nearer to the sensor. Okay. When the magnet is very nearer to the sensor, the amount of flux density picked up by the sensor is going to be larger. Yes or no? Okay, the amount of flux density picked up by the sensor is larger, and hence the value of voltage is going to be more. The value of voltage is more when the flux density is going to be larger. Okay, correspondingly, the value of, as and when you start consuming the petrol, the float will come down. Okay, when the float will come down, along with the float, the magnet will also come down. Okay, by which it is going to have a reduced magnetic flux density because of the distance. Okay, when the distance is larger, between the sensor and the magnetic flux density is going to reduce. When there is a reduction of magnetic flux density, the value of voltage is going to be reduced. Okay, now the increase of voltage or decrease of voltage depends upon what? Depends upon how close the magnet is to the sensor. Okay, which indicates that whether the magnetic flux density is higher or lesser. Okay, now this is one of the example with which we can able to understand the application of the magnetic flux density. Okay, right? Is it clear now? Clear? Shall I go further?
Yes, sir.
Yeah, right. So before we go further to the proximity sensor, we'll just summarize this. Now, what we have discussed was the Hall effect sensor. Hall effect sensor, point number 1, it is a magnetic sensor. Point number 2, it determines the magnetic flux density. And gives as the output as voltage. Okay. Point number 3, what do you mean by Hall effect? Okay. Hall effect is something, but it is a deflection of the path of charged particle from a straight line path due to the influence of the magnetic field. Okay, when there is a magnetic field, the straight line path charged particles will deflect towards the negatively charged particle, by which charge separation is going to occur. This charge separation will create what is called as the electric potential, and that electric potential is what is called as the Hall voltage. Okay, now to determine the Hall voltage Vs is proportional to Bi by T. So if you give the constant current source and the thickness of the conducting material is going to be constant, the magnetic flux density is the only varying parameter. Okay, so Vh is directly proportional to magnetic flux density. Okay, right. Now you have observed one small video regarding that and the explanation with a particular application. Okay, this is about the Hall effect sensor. Okay, now we'll move on to the second sensor called as the proximity sensors. Okay, so simple. Proximity is nothing but, very simple, understand, proximity is nothing but how close you are to me. Simple. Okay, how close the object is to the target. Okay, when I say a proximity, there exists two different things. One is the sensor, other is the target. Target are nothing but the object. Okay, now I have a sensor, I have a target. Okay, how much closer is the sensor to the target is determined by what is called the proximity sensor. Okay, basically the proximity sensor is mainly used to detect the presence of nearby object. Okay, in order the proximity sensor. Okay, so these proximity sensors are generally sensors. Okay, proximity sensors are the non-contact sensors. Okay, and they are also called as the proximity sensors are also called detects the presence of an object. When it detects the presence of an object, it says on. When it doesn't detect the presence of an object, it says off. Okay, so this is one thing. Okay, now with this one example we can consider that it's also used along with this what is called as your the presence or absence of the object. It is also used to determine what is the closeness of the object to the reference point. Okay, it is also used to determine what is the closeness of the object to the reference point. Okay, right. Now we'll understand the different types of the sensors here. Okay, one is the proximity switches. Okay, there are different types of proximity sensors are going to be there. The one by one we'll discuss. Number one is going to be called as the proximity switches. Now, in this proximity switches, if you observe, these are all the switches which are going to be there. Okay. Now the same diagram what I am showing here, okay, is also going to be present here. Here also there is a contact. Okay. Now we have two different contacts here. Okay. Switch, I will call this as switch contact. Okay. Right. Whenever this lever, whatever the lever is going to be there, is operated. Whenever this lever is operated, what is going to happen? When I apply a load onto this will come down. Okay. This will come down, and there will be a switch is going to what? Switch is going to close or open. Tell me. The switch is going to become closed. Okay. Now there are only two instances. Okay. One is opening of the switch, or closure of the switch. That's all. Okay. So there are only two actions. Are you understanding clearly? There are only two actions, on or off. Okay. Right. Now just observe this. What is that I am going to do is, I will have a conveyor. Just assume I will have a conveyor. Okay. On the conveyor, I have produced the parts. I am passing these parts onto the conveyor. Are you understanding carefully? I am passing these parts, the produced parts on the conveyor. Okay. Right. What I will do is, below the conveyor, I am going to place this device, what is called as the proximity switches. Okay. Below the conveyor, I am going to place the proximity switches, and the parts which are moving, right? The parts which are moving, when it comes, it is going to come over here. Okay, right. Now there are three different methods. One is how the closure is going to occur. The contact is going to be closed through the lever mechanism. The contact is going to be closed through the roller mechanism. The contact is going to be closed through the cam mechanism. Means when some load is going to be applied on this point, or on this point, or on this point, the closure of the switch is going to occur. Okay. Whenever the switch closes, what do you understand? Whenever the switch closes, what do you understand?
Load has been applied.
Some load has been applied. Are you understanding? Are you getting my point?
Yes, sir.
Yes, sir.
Okay. Whenever there is a closure of the switch, you should understand that there is some amount of load which is present on that lever, or on the roller, or on the cam. Okay. Now you just understand carefully. Okay. Now somewhere here, this is the switch. Okay. Just assume this is the switch I have placed. Okay. And I am having a timer here. Okay. I am having a timer here, which gives you a beep sound. Okay. Now this is moving on the conveyor, and assume this part has come here. Okay. What is going to happen when the part has come on this part? What is going to happen when the part has come above the proximity switch? What is going to happen due to the weight of this component? Yes or no?
Yes, sir.
Due to the weight of this component, the contact is going to,
It closes, sir.
the contact is going to close. When the contact closes, what do you mean by the contact close? It means you have detected the presence of the object. Okay, very simple. Okay, proximity sensors are mainly used for what? Mainly used to say whether the object is present or not. Okay, now every time the contact closes, you will detect one number here. Okay, the beep is going to come and the timer will show number 1. Okay, it goes off. Right, it goes off. When the component goes off, what is going to happen to the contact? The contact will
Open.
The contact will release. Okay, then one more component. Okay, one more component will pass on that. Okay, when the other component pass on that, again there will be a closure of the contact is going to be there. Again there will be a beep sound. And what is going to happen to this one? One is already present. Then you have a automatic timer. What is this is going to become? This will increment to the next number. Okay, are you understanding clearly? Okay, right? It also know if I observe the timer, what do I get? If I observe the timer, what is the information that I am going to get? What is information of the timer? How many product has passed this proximity switch? Okay. Now this is the method by which I can able to determine the presence of the object. Okay. Now please tell me, have you measured anything here? Have you measured anything here? Have you measured anything here?
Number of objects.
No, measurement.
No,
Count
sir.
is different. Measurement. Count, you have made the count, correct. I am agreeing that you have made the count. Have you measured anything?
No, sir.
No, sir.
Okay, you have not measured anything. Means by using proximity switches, it is possible for you only to know how many, correct? Okay, are you understanding? How many number of product has passed the conveyor? Okay, you can only know the count. Okay, so that is the objective of the proximity switches. Okay, then one more type of sensor will understand, which gives you the measurement, the value of the distance. Okay, that is called as the second one, the eddy current type proximity sensor. Okay, now observe carefully. Okay, right. Now eddy current type proximity sensor, okay, is like this. Now we have a coil carrying AC current. Okay, we have a coil carrying AC current, and we have a conducting material which is going to be present here. Okay, now observe carefully. When I bring a conducting material, nearer to the coil carrying AC current, eddy currents are going to be generated within this conducting material. Okay, I'll repeat again. When a conducting material is placed near the coil carrying AC current, eddy currents are going to be generated in the conducting materials. Okay. Now the eddy current generated in the conducting material, I am going to call it as A. Okay. Because of the why eddy currents are going to be generated? Because of the magnetic flux density. Okay. Eddy currents are going to be generated within the conducting material, that I will call it as A. Okay. Right. Now, if you bring the conducting material very close to the coil, okay, is the amount of eddy current generated is higher or lesser?
Here, sir.
Higher. Okay. When the conducting material is very nearer to the coil, the eddy current generated is higher. Okay. Right. Now, because of this coil, here also I am going to have what is called as the eddy current generated within the coil only. Okay, please understand. B is the eddy current generated within the coil, which is constant. Okay, because of the coil, because of the coil carrying AC current, eddy currents are also generated within the coil. Now, how many eddy currents are going to be there now? There are two eddy currents. One is the eddy current generated in the conducting material. Other one is the eddy current generated within the coil. Okay. So eddy current generated within the coil is going to be depends upon the number of turns in the coil, and this is going to be constant. Okay. Right. Now just observe. If I am going to bring the conducting material very closer, okay, assume like this. I am going to bring the conducting material very closer. Okay. What is going to happen to this value of A? What is going to happen to this value of A? The value of A, is it going to become A plus or A minus?
Plus.
A plus.
A plus. Okay, right. When I am going to bring the conducting material very nearer, the amount of eddy current generated is going to become A plus. Okay. Now what is going to happen now? This is higher amount of eddy current minus the value of B. Okay, right. Now similarly, if I take this conducting material away, are you understanding? If I take the conducting material away, what is going to happen to the value of A?
Decrease.
Will it increase or will it decrease?
Decrease, sir.
Decrease. Very good. Okay. Right. Now, what is that I am trying to say here is the movement of this conducting material, to nearer to the coil and away from the coil will have an effect on what is called as the eddy current. Okay. By which I am going to have what is called as another property, which is called as inertance. What do you mean by inertance? Any idea? What is inertance? Okay, remember Inertance is nothing but it is the property. Okay, inertance is nothing but it is the property of the material which oppose the AC current flowing through it. Okay, it is the property of the material which opposes the AC current flowing through it is called as the inertance. Okay, right. Means to say, that means if the value, if the conducting material is closer, if the conducting material is closer, the value of eddy current is going to be higher, and it gives you less amount of inertance. Okay, right? If you take it away, if you take the conducting material away, there will be lesser amount of eddy current and more amount of inertance. Okay, right. Now, what is this I am talking about is with respect to the proximity sensor. Okay, so what is this? This is going to be your sensor and this is going to be your object. Are you understanding? This is the coil is your sensor and this is going to be your object. Okay, right. If the object is nearer to the sensor, please tell me now clearly. If the object is nearer to the sensor, what is the value of eddy current? More or less?
Eddy current is more.
Yeah, eddy current is more. If the eddy current is going to be more, resistance offered is going to be less or higher?
Resistance is less. So.
Resistance is less. Okay, as the resistance is less, there is more eddy current. Therefore, now on the other side, I'll take this object very away from the sensor. Okay, then at that moment eddy current is going to be lesser, and as the eddy current is lesser, the amount of inertance is going to be larger. That means more the inertance, the distance between the sensor and the object. Okay, more the inertance, the distance between the sensors and the object is what? Lesser or more? More. Okay, lesser the inertance. Okay, the lesser the inertance. Okay, you can able to get that. Okay, now here the amount of distance moved. Okay, the amount of distance moved is going to be converted into what is called as the value of the inertance. Okay, now this is the object working principle of what is called as the eddy current type proximity sensor. That means in case of eddy current type proximity sensor, the movement of the conducting material, okay, will gives you what is called as a higher value of eddy current or a lesser value of eddy current. Okay, if the object is nearer to the sensor, more amount of eddy current is going to be generated, and hence there will be less value of inertance or the inductance. Okay, right. Now more and more inductance or the inertance, okay, is can be detected with the number of or the presence of the object. Okay, now this is about the eddy current type proximity sensor. Okay, right. So now just observe here, there's some definition, some note. When a conducting material is placed near a coil carrying AC current, eddy currents are produced in the conducting material. Okay, the eddy current flowing in the conducting material produces a magnetic field of their own, which act against the magnetic field produced by the coil. This results in decrease of inductance. Okay, now you just observe, this is very clear, very important. If the conducting material is nearer, higher is the eddy current and thus less inductance. Okay, if the conducting material is away, lesser is the eddy current and high is the inductance. Okay, now what is changing here? Less inductance and higher inductance. Okay, now the variation of the inductance is the measure of the displacement or proximity of the object. Okay, now how much amount of the distance is going to be present from sensor to the object, okay, can be determined with the value of inductance. Okay, right. So if it is less inductance, if the value of inductance is lesser, the closeness is going to be more. If the value of inductance is higher, closeness is not near. The distance is going to be larger. Okay, so if this is like this, inductance is, for this arrow mark, inductance is
Less.
less. Inductance is less. If I take this object away, okay, over here, what is going to happen to the inductance? The inductance is
More, sir.
more. Okay, now you just measure the value of the inductance. Okay, now by knowing the value of the inductance, you are going to say whether the object is nearer to you or whether the object is away from you. Okay, so this is the basic principle of what is called as the eddy current proximity sensor. Okay, right. Now one more we'll just go through. Okay, right. Now we have what is called as this. Okay, right. Now the third one is called as the pneumatic proximity sensor. Okay, just observe, it is called a pneumatic proximity sensor. Here also, in pneumatic proximity sensor also, you are going to measure the distance of the object with reference to the sensor. Same case. But here, the amount of distance measured is going to be lesser. Okay, now for detecting smaller distances, okay, observe, for detecting smaller distances, we are going to use pneumatic proximity sensor. In order to detect the smaller distances, I am going to use pneumatic proximity sensors. Okay, right. Now, only observe this left diagram. Okay, only observe the diagram which is on the left. Now, what has happened is, so we have a port here. Okay, we have a port. We have port over here. Now, through this port, I have supplied the low pressure air. Okay, through this port, I have supplied the low pressure air. Now, in front of the port, there are no object present. In front of the port, there is no object. Hence, the air will easily escapes out of the port. Is it clear to you? The air will easily escapes out of the port. At this point, please observe, at this point, if I am going to measure the pressure, okay, pressure at this port, okay, if I am going to measure the pressure at this port, the pressure is very, very lesser because all the air has already dragged out of the system. Are you understanding? All the air was dragged out of the system because there is no object. Now in the second diagram, I am doing something different. What is that I have done is, I am just bringing this object closer to the port. Okay, what is going to happen if I bring this object closer to the port? What is the possibility of the air to escape? Will it be more or will it be less?
It will be less, sir.
Will it be less? Where that air is going to be? Now I have placed the object very here now. Okay, it is not possible for the air to go out. Where the air will come? The air will come here. Understanding? Yes or no? The air will come here. Okay, when the air comes here, what is going to happen to the pressure at this point?
It will increase.
It will increase. The pressure at this point is going to increase. Now I will do one more thing. I will bring this object very closer like this. Okay, I will block. Okay, when I close this object like this, or when I bring the object very nearer to the port, what is going to happen to the pressure? Will the pressure still increases than the before, or the pressure reduces?
It increases more.
Okay, it increases more. Now, what is the inference that you can able to draw from here?
When the object is moved closer, then pressure increases.
Huh? Hello? What is the inference?
When the object is moved closer, then the pressure keeps increasing.
Yeah. Okay, when the object is closer to the sensor, the pressure increases. When the object is away, from the sensor, the pressure is going to reduces. Now, the distance is measured in terms of what here?
Pressure.
Right. The distance is measured in terms of the pressure. That means, in case of pneumatic proximity sensor, I am going to use what is called as the working fluid as the air. Okay, pneumatic. Okay, working fluid is the air. Are you understanding? Working fluid is the air, is the pneumatic sensor, and because of this air, which is the pneumatic sensor, whenever there is going to be the object nearer to the port, the rise in pressure is going to be more. When I am going to make the object away from the sensor, the rise in pressure is lesser. Now, what are you going to observe you're going to observe what is the amount of pressure increased. Okay, if the pressure has increased, so you have to understand that the distance from the sensor to the object is less. If there is a reduction in the pressure, means that you are moving the object away from the sensor. Okay, now if you take this away, the pressure is going to reduce. If you take this towards the sensor, the pressure is going to increase. Okay, so now conclusion is the increase in pressure or reduction in the pressure is directly proportional to how close the object is in front of the sensor or in front of the port. Okay, now this is called as the pneumatic proximity sensor. Okay, right. Then we have one more thing called as the capacitive proximity sensor. So this capacitive proximity sensor, we'll take it up in the next class. Okay, right. So we'll stop at this stage. Okay, we'll stop at this stage now, and we'll continue the class again. Okay, now here, what is that we have done today now is, okay, now to start with, we have discussed about what is the concept of the Hall effect sensor. Okay, we have discussed about the Hall effect sensor, which is nothing but what type of sensor it is? Hall effect is
Magnetic sensor.
Magnetic.
Magnetic sensor. Okay, Hall effect is the magnetic sensor. Okay, right. So then after the magnetic sensor, okay, now we understood about the working principle of that. Then we went to what is called as the proximity sensor, and then the proximity. Under proximity sensor, there are many types of proximity sensors are there. What we have discussed is the proximity switches. We have discussed. Second one, we have discussed what was called as the eddy current proximity sensor. Third one we have discussed was the pneumatic type proximity sensors. Okay, so when we come back to the next class, we'll try to understand other different types of the proximity sensor. Okay, is it clear? Clear to all?
Yes, sir.
Yes, sir.
Okay, right. So with this, we'll stop the class today. So tomorrow we shall meet. Okay, right. How about the test? It's issue clear?
Yes, sir.
Okay,
Yes,
fine.
sir.
Okay, now- yeah. Okay, fine. Okay, now I'll just end the class now. Okay. Now tomorrow we'll meet for the continuation of the other variety of the proximity sensors. Okay, right. Okay, thank you. Thank you. You can be in the same class. Professor SS will join. Okay, I think he has joined already. Okay, right. Okay, thank you.